law of large number for the random walk in random environment. And perhaps first what we should do, I forgot to do something last time, it was to prove that the convergence in the ergodic theorem holds in L1. Okay, so just let me give you shortly the argument why the sequence Sn over n is uniformly integrable. So the claim is this one, okay? If f belongs to L1 of nu, then Sn of f is uniformly integrable. Okay, Sn of f over n. Okay, where Sn of f is just f plus ft plus f t minus 1. Okay, so in fact there are two parts to this claim. Okay, the first one is that if you look at this thing, okay, let me write it. This family here, okay, it is uniformly integrable. Okay, so why? Well, simply because all this, simply because f is in L1 and f and these two things have the same distribution. Okay, but perhaps I can detail this a bit more. I mean, okay, so this is really the reason why this is true, but if you want to have this in detail, I mean, being uniformly integrable, it means that for all epsilon, there exists delta, such that mu a smaller than delta implies integral of, okay so G G uniformly integrable, G indicator of A, G mu smaller than epsilon for all G and G. Okay, being uniformly integrable, a family of functions being uniformly integrable, it means that if you integrate this function against small events, then the result is small, uniformly in the family. Okay, so particular here, I mean, let's take epsilon delta as in, okay, so because f is in L1, okay, well, because f is in L1, this is true. Okay, this is just if you want to dominate the convergence theorem. Okay, so now if you take mu a smaller than delta for epsilon delta chosen as this, what you have is that the integral of f t, indicator of A, d mu, okay, let's put an n here. Well, this is, okay, you can do a change of variable. Okay, you can, no, this thing, okay, sorry, it's equal to the integral of f indicator of t star t minus n A, and then I have T n star mu. Okay, I mean, this is just the definition of the push-forward measure. And, well, this is because T preserves measure, okay? And now this is smaller than epsilon simply because T minus 1 of A, this is equal to mu T minus n of A is equal to mu of A is smaller than delta. Okay, so, yeah, so this family is uniformly integrable. The second thing is if okay, so okay, I will not make a general statement, but basically it's that convex combinations of a uniformly integrable family are uniformly integrable. Okay, so let's show it in this particular case. So again, let's take epsilon delta such that this is true. What you have is that an A such that mu of A is smaller than delta. You're trying to show that this is smaller than epsilon, but this is smaller just using the triangle inequality. K equal 1 to n integral f t k minus 1 indicator A d mu. Okay, and yeah, by uniform integrability of f t of n. Okay, each of these terms is smaller than epsilon. Okay, and you have n terms, so all is good. So here we've taken a uniform convex combination, but this is true for all convex combinations. Okay, so if you have a family that is uniformly integrable, well, the family of all convex combination of those variables, which is a strictly larger family, is also uniformly integrable. Okay, so now let's move into the proof of the law of large number. So what was the theorem? Okay, and I will consider that the expectation of log rho 0 is non-negative. So we'll consider X, which is a random walk in random environment, starting from 0, an average random walk in random environment. And we have that the limit when n goes to infinity of xn over n is equal to v p0 almost surely, where v is equal to 1 over E0 to 1. Yeah, and by the way, because here, I mean, we are going to use the ergodic theorem for the time to reach a certain level k. You don't have this in L1 for free. I'm pretty convinced. No, okay, but yeah, the convergence is in L1 holds simply because this is bounded in absolute value by 1. Okay, and here, yes, just recall that tau k is the first time you reach tau k. You reach k. Okay, and this is for k in D. Okay, so now let me make a few remarks. So the first one is that, okay, here we have a theorem for the average random walk in random environment, but this automatically gives us a result for the quenched random walk in a random environment. So, because here, if you prove something P0 almost surely, it's the same thing as to say for P almost all omega, the property holds P0 almost surely. Okay, I mean, this is just Fubini, right? You have that the expectation of some probability is equal to 0. So this means that this probability is almost surely equal to 0. Okay, so this is the first observation. And the second observation is that assuming that the expectation of log rho is non-positive is not a lack of generality, simply because if the expectation of log rho 0, the theorem without implies that limit when n goes to infinity of xn over n is equal to v, where v is equal to minus 1 over. Okay, and the proof is just by symmetry. So you replace omega x by 1 minus omega minus x, x by minus x, and you recover the case of the theorem. Okay, and well, a third thing to recall is that the theorem is equivalent to, and this is what we are going to prove, theorem star, which is the limit when k goes to infinity of tau k over k is equal to E0 to 1. Okay, so I think I gave you the argument when V was finite. Just let me give you the argument when V is infinite. So when V was positive, okay. Let me also give you the argument when this thing is infinite. So. if E0 to 1 is equal to infinity, we have theorem star implies that tau k is larger than mk for k large enough, k larger than k0 of m for any m larger than 0. K larger than k0 of m and of the randomness. And when this occurs, what we have is that x mk is smaller than 1 over m time is smaller than x. And okay, in particular, we have this, and this implies that for all k larger than k0, and this implies that the lim sup when n goes to infinity of xn over n is smaller than 1 over n. Okay, because m is arbitrary, this has to be 0. Okay, and okay, so remember that here we have the assumption that E log rho 0 is smaller than 0. So if this is negative, then xn goes to infinity, so that the lim_inf of xn over n is larger than 0 for free. Okay, because this xn is positive for after some time. If E log rho 0 is equal to 0, then lim_inf xn over n is larger than 0 by symmetry. Okay, we can just apply the same reasoning to minus x. Okay, and this gives us the result. Okay, so yeah, I just wanted to detail this case because there is this. I mean, okay, this is easy, but you should not forget about this. Okay. Okay. So far, so good. Okay, so now what remains to do is to show that this result, theorem star, can be obtained as an application of the ergodic theorem. So what we are going to do is to construct an ergodic measured dynamical system, which is such that the increments of tau k, they are the iteration of a certain function of the of this measured dynamical system. Okay. So this is a proof of theorem star. And okay, and this is going to be a long proof. So we want to use the ergodic theorem. Okay, so what is, okay, first thing to introduce, it's omega. So omega will just be, okay, 0, 1 to the z times 0, 1, okay, to the z plus times z plus. Okay, and an element of omega I will just write it as omega psi. So I will have two parts, one belonging to this and one belonging to this. Okay, so now my measure, okay, so on this thing, I will just have my omegas. So the measure here will just be P, okay, and I will consider a product measure. And here, I will just have the uniform measure on 0, 1. Okay, so basically the distribution of IID uniform random variables indexed by z plus times z plus. Okay, so what I have is that omega x in z distributed as before, and psi j k, j larger than 0, k larger than 0, IID uniform random variables. Okay, and okay, this is not, this is mu, right? We have always called it mu, so this is mu. And I want to call this part here Q. Okay, so when I average with respect to everything which is not the environment, okay, I average with respect to Q. Okay, so now what do we want to do to conclude? Okay, so we want to construct or to exhibit, no? Well, xn. Okay, so family of variables from omega to z plus and t from omega to omega such that, okay, so first property we want is we want t to be ergodic. Okay, measure preserving and ergodic. Well, the second thing we want is we want that my family of variables here, my process xn, is distributed like the average simple random walk in a random environment. Okay, and the last thing, okay, and here I want to recall that I think we defined uk to be tau k minus 1. So, okay, implicitly, if we define this process, we also define UK as a function of the environment. Okay, so what we want to show is that the UKs well, they are, well, what was the, they can be obtained by composing tau1 with the shift operator. Okay, for k large. Okay, and if we have these three things, we have theorem star for free because okay, so let's prove that 0, 1, 2 implies theorem star. So we have that tau k over k, well, it's equal to the sum from I equal 1, y equal 1 to k, tau 1, t k minus 1. Over k. Okay, so now if we take, okay, so this is the limit when k goes to infinity. So here we are using 2. Let me put some colors. So by 2, this thing is equal to the limit when k goes to infinity of, well, this average sum. Now, using 0, okay, and the ergodic theorem, we have that this limit is the integral of tau 1 omega xi d mu. And now, using 1, okay, we know that if these things are distributed like mu, then xn is distributed like the average simple random walk. So tau 1 is just, this thing is just this. Okay, so we just have to provide this construction and we'll be done. So far, so good? Okay, so yes, so let me give you first the definition of T. So what does T do? Well, it shifts the coordinate of the environment by 1. Okay, and it shifts the second coordinate of these auxiliary variables by 1. So j larger than 0, k larger than 0. Okay, so well, these things are still IID after shifting. So T is measure preserving. Okay, this is immediate. Okay, why is T ergodic? Well, T is the Cartesian product of two shift operators. Okay, so one on R, one on 0, 1 to the Z. Okay, and the other on 0, 1 to the Z plus to the Z plus. Okay, so because the measure is a product, okay, like if you take each of the marginals, you have ergodic transformations. And now if you take the product of two ergodic transformations, it's easy to check that it's ergodic. Okay, so basically what I'm saying is that if omega 1, mu 1, T1, and omega 2, mu 2, T2 are ergodic, okay, I have omega 1, omega 2, mu 1, mu 2, T1, T2 is ergodic. Okay, whereas this notation here is kind of self-explanatory. Okay, so this is okay for 0. And now let us construct our simple random walk, okay, using this variable. So, okay, this is kind of easy. We have done it last time, and somehow, if you just want to do that, you don't need z plus times z plus here. You just need one sequence. So when we do this construction, we have to have this in mind. Okay? So there is a little trick. So I will just rewrite the formula we had last time. Okay. Perhaps in orange. I don't know. So last time, at the end of the lecture of yesterday, I constructed xn from a single sequence of variable. And the formula we had was that xn minus xn minus 1 was equal to the indicator that xi j. No, it was x plus 1 minus xn, sorry. Omega x. And minus the indicator that xi j was strictly larger than omega. Okay, and this was xn. xn. Okay, so I will just write this function as theta psi j omega xn. Okay, and okay, this time we are going to do things a bit differently. So but basically what we are going to focus on is what are the indices here we are using. Okay, this will be the important thing. Okay, so let me take. So xn omega psi is constructed as follows. So okay, we have x0 is equal to 0. Then I define xn star to be the max for m smaller than n of xn. And if x star n is equal to k and tau k is equal to m, okay, what I'm doing is I'm saying that xn plus 1 minus xn, this is equal to theta psi n minus m k and omega xn. Sorry?
Kind of last year. Are you using another construction for the xn?
Yes.
All right.
Yes.
On the xn star.
Yeah. So I'm constructing xn recursively. So what we start from x0 equal to 0, and now the next thing is A and B is xn plus 1 from xn psi omega. Okay, so if you know how to do these two things, then you have constructed the sequence, which is a function of psi and omega. Okay, and we do the same thing as before with a little twist. So the uniform variable we use here, well, we take it, well, in the case sequence we have. Okay, and we take it at a time. Okay, so what is n minus n? What is n minus m here? Well, it's the number of steps the work has performed since it reached k for the first time. Okay, so basically, you're doing two operations when you reach, when x star n increases, you do two things. First, you take your variables in, well, you shift this index, okay? You're taking your variable psi in the next sequence, and you reset the clock here. So you start using them for the first, from the first one. Okay? From the first one. Well, the first one which has index 0. Okay? Okay, so this seems like the right construction. Let us check that this really gives you something with the right distribution. Okay? So claim, and what this is really 1. For every f measurable and bounded, the integral of f so let me put this star. Okay, so this is what we are going to prove, and yes, so this already implies what we want, because if you average this with respect to the environment, okay, so if you take the expectation of star, okay, what you get is that, well, the integral of f psi omega psi nu d omega d psi. Well, this thing, it's just using Fubini. Okay, this is the integral of f omega psi q d psi. Then using this relation, this is equal to the expectation of and this is equal to this. Okay, here I'm just using the definition of the average measure. Okay, so what we are really proving is that like if you condition to the omegas and you average with respect to the psi, you are actually constructing the quench law. Okay, and okay, I will write the proof of this, but this is exactly the same as the one we had last time. So okay, we prove the claim for f of x is equal to the indicator that x0 equal x0, xn equal xn. So this is sufficient, because once you have this, you can use a monotone class argument to say that it's true for all indicator functions, and then conclude that this is true for all bounded measurable functions. Okay. So okay. So let's consider that the realization of omega is fixed, and let's look at the probability let x0 equal x0, xn equal xn. Okay, and this thing is, well, the indicator that x0 is equal to 0 times the probability that for all j in 0 n minus 1 psi j mx or mjx perhaps is in ij. Okay, where here okay, let me write this in full. Ij, it's really ij omega x, and it's equal to 0 omega xj if xj plus 1 minus xj is equal to 1. Omega xj 1 if xj plus 1 minus xj is equal to minus 1, and 0 in all other cases. Okay, this is just by construction. Okay, and yes. MJX is the max over, well, how should I write it? Yeah, okay, perhaps it's better to write it as KJX to be just coherent. KJX m smaller than j of xj. Okay, this is just by construction. Okay, so now, I mean, all the indices are deterministic. So we can rewrite this, and we have done the right thing during the construction. So what we have is really equal to delta x0 equals 0 times q x0 x1 q xn minus 1 xn. Okay, and we are good. Sorry, I forgot something. Well, okay, yeah, let me, okay, so it's equal to, yeah, perhaps. Okay, this is by independence. Sorry. Okay. Okay, because my variables are uniform and because this has the right length, okay, this has exactly this length. Okay, and we can conclude. This is E0 omega x0 is equal to x0, xn equal xn. P. All good? Okay, so now the last thing we have to show is that the shift operator does the right thing. So we have to show that tau k minus 1 is equal to tau 1 tau k minus 1. Okay, and let me call star this. Okay, so what we are going to prove is something equivalent, but on x. Okay, we have constructed x, so we'd better prove something directly on x. So let's transform this into a property concerning x. So we prove that xn composed with t k minus 1 xn plus tau k minus 1. Yeah, I think I did the wrong choice. So let's try to. I think this will be better. Because like, if not, I will have to write minus 1 everywhere, and this will be annoying. So let's do it this way. Minus k. So this is. Okay, we prove that this is true, and okay, let's show rapidly that this is equivalent to this, or that this implies this. So how do we do it? Well, if you look, you have that tau k plus 1 minus tau k is equal to, well, the infimum of n such that x n plus tau k is equal to k plus 1. Okay? This is another way of writing things. I mean, yes? This is the way that I subtract the tau k here. And while using this 2 star here, this is the infimum of n such that xn tau k is equal to 1. Okay, I'm just replacing this by its other expression. Okay, I'm putting minus k here before. Okay, and yeah, this is nothing more than tau 1 composed with tau k. Okay. With tau 1 composed with tk. Okay. And now let us prove that this thing holds. So how are we going to prove that? How are we going to prove that this thing holds? Well, okay. Let me define yn 1, which is equal to xn tk, and yn2, which is the other one. So xn plus tau k minus k. So we are going to prove two things. So the first is that y0i is equal to 0 in both cases. Okay, so for I equal 1, 2. Okay, well, there is no proof for this. It's completely obvious. The other thing is that yn plus 1 I minus yn I, okay, is equal to theta, and let me check what the index should be here. Let me. Okay, I need some space. So. Okay, I should not erase this. This is important, and I will prove that yn plus 1 I minus yn I is equal to theta. Okay, so I will have omega yn I plus k. And here I will have psi yes, so I will take n minus, well, if you want, mi. And okay, no, well, okay, let's forget about the dependence, and here I will have k plus k prime. Okay, and here y and I star is equal to k prime, and well, to k prime y and I is equal to m. Okay, so k prime, okay, here you have a plus, okay? Okay, so perhaps this thing, to simplify, I will just write this thing as theta j xn, okay? So what I want to say is that this is, okay, so this is n minus m k xn, and here what I will put is yn I plus k, and here okay, n minus m k plus k prime. Okay, and k prime here, that clearly depends on I. Okay, so so if we prove 1 and 2, we are done. Simply because 1 proves that we start from the same point, and 2 proves that iteratively the increments are the same, just by immediate induction for the 2 processes. Okay, so we just have to show that 2 is true. 1 is okay, and now let's prove 2. Okay, so let's start with yn1. Okay, so yeah, so yn1, it's okay. Okay, and let me put omega xi here. So yn1 n plus 1 minus yn1, okay. Well, it's equal to theta tk omega xi n minus m k prime. Okay. Yeah, here it's just that the k here is really k prime. Okay, let's call it k prime here, and we are good. Okay. So this is just by the definition of our construction. Okay, and now this thing is equal to theta tk n minus m k prime plus k y n I plus k, simply because this thing has the effect of shifting the indices of omega and the second coordinate of psi. Okay, so you have to put them there. Okay, why is it true for yn2? Okay, so let's look at this. yn2 minus yn. Well, it's equal to xn plus 1 plus 2k minus xn plus 2k. So I'm just applying this definition at n plus 2k. So this is theta omega xi. Okay, now what's n minus m here? Well, this is okay. Okay, so, the second thing is xn plus 2k. This is easy. Okay, and the first thing here, okay, so we are looking at things at time. Yes, so this is n plus 1 plus 2k. No, this is n plus 2k. Minus Okay, and what you have is that x star n plus tau k, I think it's equal exactly to m plus k. So, no. Okay, so this is n plus tau k minus, yes, okay. Sorry. Okay. Yeah, this is, oh, sorry, this is k plus k prime. Okay? K prime, you know, if it's a maximum of K prime, it's y and 2 star. Okay, so this is it. Okay, and now the m we are looking at, okay, so this is attained at time. Okay, tau k plus m, okay, where m is for y and 2. Okay, if m is a time, okay, at which y and 2 reaches k prime. Okay, we want the definition of m to be coherent in the two things. Okay. Okay, so here I have n plus tk minus tau k plus m. Okay, and I think we are good. Like, this thing, okay, it's you have the last coordinate is, yeah, no, okay, there is a coordinate missing, you're right. Sorry, so here there is a bracket. Here the important thing is yeah, k plus k prime. K plus k prime, because this is what you have here. Okay, and here you had x tau k plus n. Okay, and yes. So you have n minus m, k plus k prime, and this last thing you can replace it by y n 2 plus k. Okay, so just to check with full details, okay, that we are doing the right thing. Okay, and it's always good to do it on paper. If you read research articles or most lecture notes, the claim will be that this is obvious. You don't have to check it. So, yeah, do it as many times as you need to, and perhaps, and then continue doing it. Because even when it's intuitive, it's good to, I mean, sometimes, yeah, people might accept your intuition for years, and then 5 years afterward, people realize, okay, there is something wrong there in this proof, and this is embarrassing. So. Okay, and this concludes the proof of the law of large number for the random walk in random environment. So this is very good, but it would be even better if we had an expression for V. Okay, and it turned out that okay, there are some problems in statistical mechanics for which, well, you have some abstract theorem that tells you something. and you're not able to compute it further. So for instance, if you want to compute, I don't know, percolation probabilities, even in Z2, I think it's hopeless, but clearly in higher dimensions, you have absolutely no chance to do it. Okay, here it turned out that V has a simple expression. So let's prove this, and this is, okay, somehow computing the speed is easier than proving that the speed exists. Yeah, any question on this ergodic construction? Okay. So asymptotic speed of the random walk in random environment. Okay, and this is where you will see that the random environment somehow is very different from well, deterministic drift for the simple random walk. Okay, because so far, I mean, what we have seen is that you have a parameter, you tune it, and when you have a special value, it's recurrent, and if not, it's transient to the right or transient to the left, which is exactly the same thing as the random walk with constant bias. So let's start to see things that are a bit different. So this is a theorem. All that we have seen concerning the random walk in random environment up to now is due to Solomon, okay, in the same paper of 75. Okay, and what's the theorem? Well, it is the following. So the limit when n goes to infinity of xn over n is equal to v, p0 almost surely, where v equals, so 1 minus the expectation of rho 0 divided by 1 plus the expectation of rho 0 if the expectation of rho 0 is strictly smaller than 1. 0 if the expectation of rho 0 is larger than 1 and the expectation of rho 0 minus 1 is larger than 1. And minus 1 minus the expectation of rho 0 minus 1 over 1 plus the expectation of rho 0 minus 1 if the expectation of rho 0 minus 1 is strictly smaller than 1. Okay, so if you want to know if your random walk has positive speed or not, you just compute well this thing, and you're able to figure out whether you have zero speed or if you go to infinity or minus infinity with positive speed. Okay, so first, yeah, before trying to give some elements of proof, let's make a few observations. So, okay, when this is smaller than 1, this thing here is positive. So this implies that, in particular, xn goes to infinity. So this should imply that the expectation of rho 0 is non-negative, and this is true just by Jensen. Okay, so. Remark 1. So if then the expectation of log rho 0, it's smaller than log of the expectation of rho 0, smaller or equal to 0. Well, it's strictly smaller than 0. Okay, so we don't have some immediate disproof of the theorem, which is good. Okay, so this is one thing. And the other thing is that, well, okay, because we are applying Jensen to a function which is strictly convex, okay, in the sense that it's convex everywhere. For Jensen's inequality to be an equality, you will need the distribution to be trivial. So therefore, if and omega non-constant, okay, we have that okay, so this means that you can have case of, so we can have xn go to infinity, and xn over n goes to 0. Okay, so transience and ballisticity are not the same thing for random walk in a random environment. Okay, and perhaps the last observation is that yes, this thing is completely symmetric. Okay, so 1, 2, 3. So 3 is just 1 with omega x replaced by 1 minus omega minus x. Okay? Because here what you have is really that rho of 0 is equal to 1 over rho 0. Okay, so we are just going to prove this first. Okay, so let's just take a 2-minute break before going to a technical proof. So. let's go back. Yeah, perhaps a last comment on the result. Okay, this behavior on the middle, we have seen that, this can happen even when you're recurrent, when you're not recurrent. And okay, let me emphasize on this, showing that this is not really exceptional. So, for instance, take an example. So let's consider an environment where P, the probability that omega 0 is equal to 3/4 is equal to P, and the probability that omega 0 is equal to 1/4 is equal to 1 minus P. Okay, so you have that the expectation of log rho 0 is equal to 0 if and only if P is equal to 1/2. Okay, just because if you look at this thing, this is strictly decreasing in P. Okay, and this log, it can be equal either to 3 or 1/3. Okay, and but okay, there is a non-trivial interval around 1/2 where E0 is strictly larger than 1, and P rho 0 minus 1 is larger than 1. Okay, so when you make P vary, okay, when P is equal to 1, for instance, your walk will be ballistic to the right. Then when P goes below a certain threshold, it will start to be, basically the speed will decrease, okay, from basically being equal to 1/2 to being equal to 0. And this will reach 0 at the value of P, which is not 1/2, but which is strictly larger than 1/2. Okay, so if you look at like this is V, this is P, what you have is something like that. So this is 1/2. This is, well, this is 1/2 as well. Okay, and what you have is something like this. This is 1. You have something like this. Okay, and well, in fact, you can plot exactly what this function is. So you can say whether my drawing is good or not. Okay, okay, so I think later on we will try to understand why this slowdown occurs. But what we will do today and perhaps also on next Tuesday is prove this theorem, and to compute V. I mean, what we really need to do is to compute the expectation of τ1 under the anneal measure. Okay, to show that this is the inverse of that. Okay, and we will just deal with this case 1 and 2. And in fact, what we will do is really compute the expectation of τ1 under the quench measure. Okay, so what will be the right thing to do? Well, proposition. If the expectation of log rho 0 is equal, is smaller or equal to 0, okay, let's yes. Okay. So yeah, we are going to assume this, and we are going to prove that E omega tau 1 is equal to 1 over plus some k equal 1 to infinity, 1 over w omega minus k, and then you have rho 0 rho minus k plus 1. Okay, so in particular, yeah, so yeah, I think this result is also true. I'm pretty sure this result is also true when the expectation is equal to 0, but somehow it's a bit annoying to prove. I mean, okay, when this is equal to 0, this sum diverges to infinity. Okay, and we already know. Okay, but somehow, I mean, the argument we are going to use in the proof is going to rely on this. So, okay. So, okay, why is this? Why is this true? Okay, this is because rho 0, rho minus k decays exponentially. Okay, why does this decay exponentially in k? Well, because if you take the log, it decays linearly in k, just because of the law of large number. Okay, and not needed but convenient. This thing is not super nice because it depends on k, but it's bounded because of our uniform ellipticity assumption. Okay, so why does this proposition imply our theorem? Okay, so proof of the theorem. Well, if the expectation of log rho 0 is equal to 0, then V is equal to 0 because xn visits equals 0 for infinitely many n. Okay, I mean, you know that 0 is a cluster point for the sequence just because the walk is recurrent. And now you know that the sequence converges because of what we just proved, yeah, the fact that V exists. So therefore, V has to be equal to 0. Okay, because we know that V exists. Okay, and if the expectation of log rho 0 is strictly negative, then this thing, well, it's equal to the expectation of E0 omega to 1, okay, just by definition of the average measure, average law, and well, this is equal to, so now I will use independence, so 1 over, so yeah, so it's the expectation of omega 0 minus 1 times the sum from k equals 0 to infinity of the expectation of rho 0 to the power k. Okay. Here I have k independent terms, and they are independent of this. And this is a k equals 0 term in the sum here. Okay, so and this is it, right? So we get 1 over v is equal to this, and this is equal to, okay, this gets us y minus expectation of rho 0. Okay, so here I'm using that the expectation of rho 0 is strictly smaller than 1. And above I get, well, the expectation of this, but the expectation of this is 1 plus the expectation of rho 0, okay, because omega 0 is equal to 1 over omega 0 is equal to 1 plus 1 minus omega 0 over omega 0. Okay, and well, this is for the case where this is finite, and if this is, where this is strictly smaller than 1, if this is larger or equal to 1, well, this sum is infinite. You have this immediately. Okay, so yes, it's not. So I won't have the time to fully prove this, but what can I do is to do the kind of cheap proof, and then we will repeat it next time, but rigorously. Okay. So the idea of the proof is not super complicated. We want to do the same thing as what we did when we tried to get estimates for the heating time probabilities. You know, we had this kind of gambler's ruin problem to solve, and we had a relation, okay, between the probabilities starting from different starting points. Okay, so here we are going to do to get to play the same game. Okay, we are going to condition to the first step, see what happened, and get a relation on different things. So let's do this. So this is the proof of the proposition. And okay, it's not rigorous, but it's not very far from being rigorous. So. In fact, okay, yes, perhaps I will just write the proof, and at the end you will tell me why it's not rigorous. Okay, so what's this expectation? Well, it's the expectation of tau1 condition that the first step is to the right times the probability that the first step is to the right. Okay, plus the expectation that of tau1 times the probability that the first step is to the left. Times multiplied by the probability that you're going to the left. And okay, we have two terms. The first one is, okay, what's the value of this? 1. Okay, this is good. Okay, so we have, the second term is a bit, so let me call, I don't know. This is the equality here. Yeah, let's now say something about this. So what's well, this thing. Well, if you condition to this event, what you see after time 1 is just a random walk starting from -1. So what you get is, well, the expectation of tau1 starting from -1 plus 1. Well, because you've already performed one step and you have to count it. Okay, and this thing you can rewrite it using the strong Markov property. Okay, this is 1 plus, well, the expectation that from -1 you reach to 0 plus the expectation of eating 1 starting from 0. Okay? If I want to reach 1, well, first I have to reach 0, and then from 0 I have to reach 1. Yeah, you already see that all of these reasonings by Solomon, and not only they only work in one dimension, but they only work for nearest neighbor, because you use very strongly the fact that you have to pass through every side. I mean, theoretically, I think it's adaptable to non-nearest neighbor case, but it really becomes a mess because the equations become much less nice in that case. Okay, so now, if you re-inject this into this relation, so re-injecting into this, what you get is that, well, okay, you have this thing here on both sides. Okay, so what you have is that, well, 1 minus omega 0 times the expectation. So omega 0 times the expectation. It's equal to omega 0 plus 1 minus omega 0, and now I have to take these two terms. Okay, the third one, I've already transported it to the other side. So I get 1 plus the expectation starting from minus 1 of 2, 0. Okay, and now you divide everything by omega 0, so you get this. 1. Okay, yes, so yeah, okay, basically you can add these two things, and this gives you 1. So here you have 1 over omega 0. Here you have 1 minus omega 0 divided by omega 0. And here you have e minus 1 omega 2, 0. Okay. Now, what more? Yes, so now the idea is you want to iterate this thing. So what you want to do is to use what you just did, but to get an expression of that and to re-inject it. Okay, so I mean, this is just this for the shifted environment. So, okay, so by shifting, you get that e minus 1 omega to 0, it's equal to 1 over omega minus 1 plus rho minus 1 times the expectation. Starting from minus 2 omega of tau 0. Okay, so I'm reinjecting this, and I get that E0 omega to 1, it's equal to 1 over omega 0 plus 1 over omega 1 times rho 0 plus rho 0 rho minus, oh, yes, okay. Rho 0 rho minus 1 e minus 2 omega tau minus 1. Okay, and then I can iterate this. And basically what happens when I iterate is that, well, I will get one extra row in my last term, and I will get an extra term appearing. So this is equal to 1 over omega 0 plus 1 over omega minus 1 rho 0 plus 1 over omega minus 2. Well, okay, let's put the dots here. Plus 1 over omega minus k. Rho 0 rho minus k plus 1 plus the sum plus, the rho 0 rho minus k e minus k minus 1 to minus k. Okay, basically here we are taking the dependence. We are looking at the dependence to the environment up to minus k, and this take care of the rest, right? This take care of the cost of all the visits you make left to minus k minus 1. Okay, and this is where the dependence in the other omegas is here. Okay, and then you let k to infinity, and you get that this is, well, 1 over just what we want. Okay, so why is this not a proof? Okay, so this is true. This decays exponentially. You would have to prove that this does not grow exponentially. But this is not. See, somehow I think this is not the most important part. There is something which is more important. So basically, at one point here, okay, we have assumed that the expectation here is finite because we've subtracted something. Okay, so there are 2 minutes. The way to solve things. Okay, I will do it back next time because. But the way to get out of this mess is. Well, if you put, okay, basically, if you put this here and this here, you get this formula with this here. Okay, this hat just means you take the max between the two quantities. Okay, and the reason is simply because, well, okay. Basically, when you're adding the plus 1 and you're taking the sum here, things go in the right direction, right? If you're capping things with m, things are going in the right direction. And now everything is rigorous because this is bounded, so this has finite expectation. Okay, so this gives you, okay, and now, okay, this also solves your problem. This goes to 0 almost surely. So what you get is that this thing is smaller than this. So in particular, it's finite. Which means in particular that this step is rigorous. Okay. Which means in particular that this is true for every k. Okay. So that, yeah, the lim sup is smaller than this. When this is smaller than this, and this is also larger than that, so you're good. So, in fact, this is never a problem. You never need to worry that this goes to 0, just because you're just using this thing for the lower bound in the end. Okay. I mean, when you use it for the upper bound, it's with the truncated version, so you're good. Okay, so this was a bit fast, so I will go back to this bit next time, and yeah. So I think then the next thing we are going to do is to look at the central limit theorem. So to see at which condition you have a central limit theorem. So this will allow us to understand a bit better what this criterion about the expectation of rho means. And the central limit theorem is also something interesting because you will have two different theorems, two different results for the quenched and for the annealed walk. Okay, because basically when you have something holding almost surely then quenched and annealed, I mean, they are the same kind of results. If you have a convergence in distribution, well, converging in distribution for the quenched law or for the annealed law is not exactly the same. Okay, so thank you, and